Hello and welcome back to Basic Topology, the video series where we talk about the fundamentals of topological spaces. And indeed, in today's part 3, we will clear up what we mean by closed sets and we will define the so-called closure. But first of all, I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can download a lot of additional material by clicking the link in the description. And now for the start of this video, we should quickly recall the definition of a topological space Xt. Now from the mathematical point of view, this is actually quite simple because X is just any set and T a collection of subsets. So as often we just have a set with additional structure, where the additional structure now comes from subsets of X. Moreover, you already know this set T is called a topology on X, and it has to satisfy 3 rules. And just for the sake of completeness, I copy them here because we have already discussed them in detail in the last video. So this makes a topological space, and now we can simply sketch it like that. So it's the set X, and maybe an element from T could be this set here. So you would say this is a set A in T. And now we have already learned that the sets in the topology we call open because they should act like that. And if you apply that to a metric space, then you know that open should mean that the boundary of the set is not included in the set at all. This makes the set open in the metric sense, but it also means that the whole boundary is included in the complement of A. And in fact, a set that includes the whole boundary is what we would call a closed set. However, here please note, at the start, we don't have the knowledge about a boundary or anything that a metric space could give us, therefore we need to define the term closed. And there it turns out that the description with the complement is already perfect. This is how we will define a closed set. In other words, when we know what open means, we also know what closed means. So we just start with a general topological space and then we take an arbitrary subset of X. And now we say that this set B is closed if the complement of B in X is an open set. And there you could just write X without B, so X minus the set B lies in the topology T. And that's already it. This is what we can do in a topological space, and it totally fits with every definition of closedness in a metric space. So what you can remember here for the two concepts open and closed is that we have an inherent duality between them. And moreover, because of that, you immediately get 3 properties for closed sets as well. First, since the empty set is open, the whole set X is definitely closed. And on the other hand, since the whole set is open, the empty set as a complement is also closed. So this first property looks exactly like the first property for the open sets, and it also tells us something immediately. Namely, a subset of X can be open and closed simultaneously. So the two concepts here don't exclude each other. However, the properties are definitely not the same because the second and third property here will be translated with the complement in mind. This means if we have a closed set B1 and B2, then their complements are open sets and we can look at the union of B1 with B2. Simply because the union here will be the intersection of the complements. In fact, this is quite easy to see. Here we have B1 and there B2. And then the complement of the union is just the intersection of the 2 other complements. And we know from the second property that the intersection of 2 open sets is open again. So by definition, the union of 2 closed sets stays closed. So we need a finite assumption for the union there, but for the intersection, we can go to a general index set I. So we have possibly infinitely many closed sets Bi here. And then we can just look at the whole intersection of all these sets. And then as before, we can go to the complement and apply the third property for open sets. So we can remember an arbitrary intersection of closed sets is always closed. And you see, showing that is quite simple, it immediately follows from De Morgan's laws from set theory. And maybe to remember it, let's quickly look at the real numbers with the standard topology. There we could say that the interval from a to b is closed because the complement is open. The complement is simply from -infinity to a, where a is not included, and union with b to +infinity. We might know that these intervals are open, and the union of open sets is also an open set, so this will be a closed set. So calling that a closed interval is totally fine if we deal with the standard topology. Indeed, if we deal with a different topology, it could definitely happen that this interval here, this set, is not a closed one anymore. But here it's correct, so let's go to an intersection of closed sets. Let's consider the interval from -1/n to +1/n. And then n is chosen as my index, and then we can go through all natural numbers. And just to be clear, 0 is not part of the natural numbers here. And then forming the intersection, we see that the only point that remains is the origin 0. And of course, it's not hard to see that this singleton is also a closed set. On the other hand, we know that in the standard topology, it's not an open set as well. This is worth mentioning because we could do this whole intersection with open sets as well. Indeed, if we have the open intervals here, we will not change the intersection at all. Also, just the origin remains. The outcome is already what we knew, and please keep that in mind, an arbitrary intersection of open sets does not have to stay open. Okay, so this was R with the standard topology, but you know that the properties for closed sets hold in general. And these allow us to extend any set in our topological space to a closed set. So as before, we work in a general topological space Xt, and then we look at an arbitrary subset M. So it's just a subset, so it does not have to be closed, open, or anything. But we will look at the special closed set, and we will call it the closure of the set M. So the name already suggests that we extend the set until it's closed. And the common notation we use for that is M with an overline. Now obviously you could just take any closed set B that extends our set M. The only requirement here is that B is closed, and we already know that the whole set X is closed. Therefore, if we put all these possibilities into a set, it's definitely not empty. And there you see, the only thing that remains to do here is to form the intersection of all these possibilities. And as before, we know the outcome of an intersection is also a closed set again. And in fact, this intersection guarantees that we get the smallest possibility out. So maybe as a remark, if you don't like this intersection symbol without any index set, we can also write it like before. And maybe there we call the index set curved A. And then of course curved A has to be exactly the set from above. So the meaning does not change here, it's just the standard intersection of a collection of subsets. But still, the important result is that overline M is the smallest closed set that still contains M. And indeed, the existence of that set is proven in this definition of an intersection. And now to finish this video, let's look at a nice example. Let's simply take the real number line again, but now not with the standard topology. Namely, let's take a much rougher or a much coarser topology. There I just mean that it contains less elements than the standard topology. However, we cannot change the empty set and the whole real number line because these always have to be open sets. But now I only want to add some special intervals as open sets. Namely, I just want to have symmetric intervals from -a to +a. So every positive a is allowed here, and these are the only open sets. And now I think it's a good exercise for you to check that this collection of subsets satisfies the three properties of a topology. It's not so complicated, and then you know that these are all our open sets, which also define the closed sets. By definition, these are just the complements, so the empty set and R stay the same, but then we have intervals from -infinity to -a, union interval from a to infinity. And also here, this holds for any A which is positive. And now we can consider a subset M in R, and let's say it's the interval from 2 to 4. And by looking at the topology, we can immediately conclude that this one cannot be an open set, and we also know it cannot be a closed set as well. And since it's not closed, we can immediately conclude that the closure of M, denoted by M over line, is definitely a bigger set. So the question is, how can we find the smallest closed set that still contains M? In general, this can be quite hard, but here we can immediately write it down. In the case the closure is not equal to the whole real number line, we can write it as a set from -infinity to -a, with the union from a to +infinity. And now since this one needs to contain M, we definitely have to choose a smaller or equal than 2. And obviously exactly 2 gives us the smallest set, which means that this is our closure of M. So there you can already see how we can work in a general topology, and why this is useful we will see soon. But first I want to discuss some more definitions which will be useful later as well. Therefore let's define a general compact set in the next video. So let's meet there again and have a nice day. Bye bye.
God.